right, so exam 1 is going to be chapter 10, 11, and 12. So this is the content for exam 1, these 3 chapters. So we come to alcohols. And remember, when we come to a new class of chemical compounds, organic compounds, we talk about their properties. What are alcohols? What's kind of some of the common behavior of alcohols? And how do you name alcohols? And how do you draw alcohols if you're given the name? And how do alcohols react? Okay, so that's the 4 things we need to get through. We'll probably get through 2 of those, and Monday we'll concentrate on reactions. So, what are alcohols? Alcohols have an OH group on them. That's the characteristic thing of alcohols. So, here's simple model, 2 carbons. Instead of another hydrogen right here, we'd have ethane. We have an OH group, an oxygen and a hydrogen. So here's where we are. We're moving away from just carbon and hydrogen to carbon, hydrogen, and oxygen. And actually, chapter 12, 13, and 14, the only other element we're going to add is oxygen. And we're going to get a whole bunch of classes of organic compounds, depending upon where the oxygen is, how is it in that molecule, and how does it behave. But here's the first one, alcohols. And when we write, just in case anybody is confused about this, when we write this, we're just saying R is any organic molecule. It could be 1 carbon. It could be 2. It could be a benzene ring. All right? It could be an isopropyl group, R. So that's what we're saying, general formula. So there's always an OH in an alcohol. And then what else? Well, there's thousands of different kinds of alcohols. Properties. Okay, here's where we're going to, this is looking at just a pure alcohol all by itself. And this is an alcohol in water. Jennifer, could you turn this light off for me, please, the front light? Thank you. Okay. These are very different from alkanes and alkenes. Remember, alkanes and alkenes were nonpolar. Remember? We use that word, nonpolar. Alcohols are polar. Why are they polar? Because the OH bond is polar. Electrons are attracted to the oxygen strongly enough that this appears somewhat positive and the oxygen appears somewhat negative. It's not an ion. It's not like sodium chloride where you actually have ions. You have a covalent bond but unequal sharing of the electrons. So you get a polar bond which brings some polar character into the molecule and allows the seemingly negatively charged oxygen to be attracted to a hydrogen on another alcohol molecule. So this little dotted line right here is the hydrogen bond. That's a hydrogen bond. We don't draw it with a solid line because that's not a covalent bond. They're not sharing electrons. There's an electrostatic attraction towards the oxygen, towards the hydrogen on the other molecule. It isn't as strong of an attraction as that right there. It's going to take a whole lot to get that hydrogen off of that oxygen. But we could heat this up and break that hydrogen bond. All right, so here's the pure alcohol. Hydrogen bonding with another molecule of itself. Now you throw that, here's the alcohol, there's the R group, whatever R is, 1, 2, 3, 4 carbons. Here's the R group. Now you throw it in water, same thing can happen. The oxygen on the alcohol can hydrogen bond with a hydrogen on a water molecule. the oxygen on the water molecule can hydrogen bond with a hydrogen on an alcohol. Those are hydrogen bonds. Although they are not as strong as bona fide covalent bonds, they are very important. When things can hydrogen bond, when molecules can hydrogen bond with themselves or something else, it affects their properties in dramatic ways. Okay, now let's take a peek here. Now what I want you to look at is this molecule and compare it with this molecule. This is an ether. We'll get to this at the end of the chapter, but I won't worry about it too much. When we get there, we'll mention it. But just not to get confused with too much data here, compare this with this. Now what is similar about these is their molecular weight. I don't know that offhand. I could probably, 12 and 12 and 12 is 36, and 9 is 45, 47. So that has a molecular weight of about 47 grams per mole. 12, 12, and 16. So 24, 34, 40, 45, 46. So weight of the molecule is almost identical. Very, very similar molecular weights. But look at this. This is approximately, let's just round that off to minus 40. And let's round that off to 80. We don't have to worry about the exact numbers, but the ballpark. What's the difference here? It's a 120 degree difference in boiling point. That's a huge difference for two molecules that have about the same molecular weight. And why? Because this molecule does not hydrogen bond with other propane molecules. This is propane. It doesn't hydrogen bond with other propane molecules. There's very weak intermolecular forces in propane. So you heat it up and the propane starts getting energetic and I'm out of here. And it evaporates. It's gone. It's not attracted to the other propanes, but not here. In order for this to evaporate, it'd be good to have these as dotted lines, but for this molecule, let's say this is the top of your beaker and you're heating this up. Before that molecule can evaporate, the energy has to overcome that attraction. And you got to heat it up another 120 degrees before that happens. Okay? Doesn't destroy the molecule. That molecule goes off as a molecule, but you now added enough energy at 80 degrees centigrade. You've added enough energy to overcome that attraction. Well, I mean, if you just take this, here's ethane. Here's ethane. It's a gas at room temperature. It's a gas. It's already boiled. You know, boom, gone. It's gone out there. It's a gas. But you take this is the alcohol in alcoholic beverages, ethanol. This is a liquid. This is a liquid. Put it in a glass, sit it there. Alcohol. It doesn't disappear. Can't do that with ethane. Ethane is it's just a gas in the glass. All right? Okay, now it affects solubility. Alcohols are more soluble in water. So again, there's a lot of data on this chart. So look at this and this for right now. We'll come back and look at two others here in a minute. So there is ethanol. I just drew that a minute ago. 2 carbons and an OH. 1, 2, 3, 4 carbons and an OH. So that's ethanol. This is butanol. Ethanol, very soluble in water. Butanol. Now, what I mean by very soluble, you could put 100 grams of ethanol in 100 milliliters of water and it will be a solution. It will dissolve 100 grams of ethanol. It'll dissolve 200 grams of ethanol. There's no point at which the water and the ethanol won't be soluble in one another. We use the word there, the word we use is miscible. It's just saying they are so soluble, there's no limit to their solubilities in one another. Ethanol and water. Miscible in water. Butanol is not. 7 grams. That's how much you can dissolve in 100 milliliters of water. You put 10 grams in there and 3 grams are going to be floating on the top of the water. They won't dissolve in there. There'll be butanol in the water, but there's also butanol that's not in the water. Follow me? It'll phase separate. All right, so what's happening? As you increase the chain length, here's an OH, here's an OH. It's attracted to water. It's polar. This is the polar end of the bond. But you're starting, as you increase the chain length, you're starting to make that molecule more and more non-polar. This part of the molecule is not polar. There's no oxygen over here. There's no hydrogen on an oxygen. That's what really makes it polar. There's no OH group over here. So as it grows, as it gets longer and longer and longer, the molecule itself becomes more and more non-polar. All right, so let's see what we got here. We're looking at we're graphing solubilities of alcohols. That's the blue line. The blue line is alcohols. We're graphing their solubility as a function of how long the chain is. So this right here would be ethanol. This right here would be that butanol that was on the previous slide. 4 carbons long. Number of carbon atoms in the molecule, 4. All right, there's other thing. I won't draw the whole structure, but there's the longest chain with an OH on it. 5 carbons, 6 carbons, 7 carbons. There's butanol. It's at about 7 grams per in 100 milliliters of water. It looks a little bit more like 7.9 or 8, but that's it. The line is going way up there because when you get to propanol, it's really high, and these two, it's infinite. You can have infinite number of these alcohols in water, so there's no limit to it. It goes up asymptotically. 4 carbons, 5 carbons, a little over 2, 6 carbons, about 1, 7 carbons is the same as heptane. So hexanol has the same solubility as heptane. And 1-heptanol is not heptane, so how do I say that? Same as heptane. And then you go on. 7, 8, 9, 10. So once you get up to 7 carbons long and longer, the molecule is just as nonpolar as an alkane. So I said that alcohols are more soluble in water than alkanes. That's true, but it also depends on how long the chain is for the alcohol. So let's just get it. With 1 OH, as chain length increases, solubility does what? Decreases. All right? Why is that? Well, as the chain's getting longer, the molecule's getting more nonpolar. Oh, I wanted to point out one other quick thing. This will help you in the homework. If you compare now this molecule, no, you're not comparing that molecule. You're comparing this molecule with this molecule. Notice 1, 2, 3, 4 carbons, 1 OH. 1, 2, 3, 4 carbons, 2 OHs. It's more soluble in water. Chain length is the same. Chain length is the same. But the second one has 2 OHs. And really, remember, OH is what's making it polar, making the molecule polar. And now it is very soluble, just like ethanol. And if you take a look at it, if I hide that there, that looks like ethanol. That looks like ethanol on the other side of it. There's an OH for every 2 carbons, just like in ethanol. And it's got enough polarity in the molecule that it's very soluble. All right, so you can only say what we said on that slide if you have only 1 OH in it as the chain length goes on. So you'll have a problem on the homework that has you kind of noodle that. You'll see 2 molecules there and you'll come back to this slide. Okay, now let's get into naming. Naming, and then we're going to classify alcohols. Naming. There's some common names like this. A real common one is isopropyl alcohol, or it is called isopropanol, or it is called rubbing alcohol. Okay, this is an alcohol that has all kinds of names. All right, those are all common names. Methanol, ethanol, propanol. We're getting into IUPAC names, and actually propanol, there's a 1-propanol, and there is a 2-propanol. So by the time you get up to 3 carbons, 4 carbons, 5 carbons, you have to start saying, okay, where is this OH? Which carbon is it on? To actually use the IUPAC system. All right, a couple examples. Here's one simple example. 4 carbons long. Again, you're using the same rules you used in chapter 10 and 11, and we're just now trying to figure out how do we accommodate an OH in the name. And the way we're going to accommodate an OH in the name here is we're picking up the OL from the word alcohol, and we're tagging it on the end of the name. So if your mouthwash at home says there's menthol in here, menthol. You say, well, I bet you menthol's an alcohol. And I bet you're right. Okay? So when you see an OL on the end of an ingredient, it's probably talking about an alcohol. Whether it's giving you the common name or the IUPAC name, it's probably what it's talking about. So longest chain, rule number 1, 4 carbons long. Butane, we drop the E and we add OL, we get butanol. Where is that all? That all is an OH group. It's on the 2nd carbon. And what else is on there? There's a methyl on the 3rd carbon. So 3-methyl-2-butanol. All right, tell me what you would do with this. Name that molecule. Okay, we see it. I'm hearing a 2-methyl 4-hexanol. Okay, so I hear someone saying no. Give me another, Kevin.
So it'd be 5-methyl 3.
Okay. Okay, so Kevin, if we started at that end, what would the... So you still want to call it hexanol?
Yes.
Okay, hexanol.
Yeah.
So Kevin?
5-methyl.
Okay, all right? This proves a good point. Now notice here, we got the OL in the parent name. So whatever that functionality is, you want to count from the end closest to that functional group. Okay? That takes precedence over the methyl. Yes, this methyl is closer to that end, but that's just a substituent on an alcohol, hexanol. We're going to pick up the substituents after we locate this thing. And so this is closer to this end. That's carbon number 1, 2, 3, 4, 5. Okay? All right. Everybody good with that? So stick with that. This example up here didn't make that clear. But that one I hope makes it a little bit clearer. Before we look at that slide, let's just look at the one that has just an OH on it. There's a 6-membered ring. It's not aromatic. It's an alkane. It's a saturated ring. So that without the OH, it would be cyclohexane. So we cyclohexane. What do? We drop the E and we add OL. And it's called cyclohexanol.
So what about the 2-hydroxybutyl?
Just one second. You can see I'm not putting any 1 in here. Okay? That is carbon number 1. That OH is on carbon number 1. But no matter where that OH was, that is the carbon that would be carbon number 1. All right? Doesn't matter where that OH is. And no matter where the OH is, I could rotate it around and drop it on top of that one. All right? That's a uniform hexagon. So it doesn't matter where the OH is, that's carbon number 1. So this is really what it is called, but this is unnecessary. The 1 is unnecessary. Okay, what's your question?
Like if you had a different structure that had 2 hydroxyls or more.
Yeah, we could talk about that. We have a slide that shows you how to name something that has 2 hydroxyls on it. But if there are 2, now you have to use numbers. And you got to use 2 numbers. You got to tell me where they both are.
Well, wouldn't the first one always be 1?
Yeah, 1, 3, 1, 4, 1, 2. Yeah. So when there are 2 of them, then you got to get into numbers. So here's a case here where we have cyclohexanol. It doesn't have another OH on it. It has a methyl group on it. This is carbon number 1 because we're going to key off of that OH. That's where we're going to start counting carbons. 1, 2, 3. So it's 3-methyl cyclohexanol. Now I still don't need the 1 because I know wherever the OH is, that's where carbon number 1 is, and the methyl is going to be 2 carbons over from it on the ring. So that's 3-methyl cyclohexanol. That's 3-methyl cyclohexanol. Okay? Doesn't matter how it's drawn. You're not going to count, you don't count clockwise to get over here. You count the shortest distance.
The shortest, the smallest number.
Right. You want to have the smallest number in the final name, and so that's 3-methyl-cyclohexanol. We will get to 2 OHs here in a minute, and how do we handle 2 OHs. Okay, let's take a look at this one. You want a 3x5 card of this. Here's your 3 carbons. The OH is in the center. Now, if I didn't have an OH there, you'd say, oh, that's an isopropyl substituent. Well, it's an isopropyl substituent with an OH in the middle. So it's isopropyl alcohol. Or isopropanol, or rubbing alcohol. Now the other thing you're going to want on your 3x5 card, you should probably have all those names on there. Isopropanol and rubbing alcohol. But any alcohol you're given, you should be able, you should be able to figure out what the IUPAC name of it is. So what's the IUPAC name of that? Pretend you don't know all those common names. What does IUPAC call it? Let's see, Leah has answered, Kevin has answered, someone else. Okay? Can't have them hold down the class. What's the parent name of it? Propanol. This is the way to proceed through these. Longest chain is 3 carbons long, so the parent name is propanol. What else does it need? 2. The OH is on the second carbon, okay? So that is 2-propanol. So on your 3x5 card, you should have all these names on one side. You kind of know, you should know that's the IUPAC. If you don't, label that as IUPAC. On the other side, you have that structure. Or draw out the structure however you want to, but just so that you know what isopropyl alcohol is.
Wait, and that's it? It's just 2-propanol?
That's it.
That's it?
That's it. That's the full name. 2-propanol. Did we leave anything out?
No.
That's it. That's the name. Okay, this is another 3x5 card. This is T-butyl alcohol, or it's tert butyl alcohol, or tertiary butyl alcohol. Well, I mean, you might find it called T-butanol or tertiary butanol. So it could just use the word butanol or butyl alcohol. Tertiary. We're going to get into the words primary, secondary, and tertiary in just a minute. But this is a tertiary alcohol. And you'll see it come up on the slides. Okay, IUPAC name. What's the longest chain? 3. So with the parent name? Propanol. 2 what? 2-methyl. 2-methyl. It's a substituent. 2-propanol. All right? You can see the 2-propanol in there, but we replace that hydrogen with a methyl group. So now it's 2-methyl 2-propanol. Okay, just a couple common alcohols. Methanol, back in the roaring 20s, 1920s, when alcohol was illegal, people were making their own alcohol. Some people made this, which is also called wood alcohol. Under some conditions, I don't know exactly how you make wood alcohol instead of ethanol, but you also, through a fermentation process, can make wood alcohol, but it is poisonous. It can be lethal. You drink too much of this, it'll kill you. You drink not quite so much to kill you, it will make you blind. Right? Where you do see this, you go into a restaurant and they have these little glass things with a wick in them and they're burning. That's usually methanol in there, burning. Burns real nice and clean. It burns well. As a matter of fact, in the 1107 lab, will you burn methanol? I think so. I think you burn methanol. Yeah. And you'll see how nice and clean it burns, just like in the restaurants. So it is used as a fuel. You can use methanol as a fuel. It is toxic. There's ethanol, the alcoholic beverages made from fermenting sugars. Enzyme action. Where is that coming from? From bacteria. Bacteria, living organisms, are providing the enzymes to convert the sugar into alcohols.
Should we make flashcards compared to
Yeah, probably. So it's ethanol or it's ethyl alcohol. So this is its common name. Here's isopropyl alcohol. We talked about that. This is your isopropyl, or they're calling it secondary propanol. You'll see that secondary. It's a disinfectant, so you can wipe the skin and kill the bacteria. I don't know if that's what nurses use before they give you a shot. If you go in for blood, to give a blood donation, they usually wipe you with something stronger than this. I forget what it is, but different. That orange stuff that they do is stronger than this. But this is a good little disinfectant. It's an industrial solvent. This is antifreeze ethane diol. Okay, so here's an example of you've got two OHs on two carbons, and it is you put in a diol. So it, instead of like you would with a dimethyl or a diene, hexadiene, this is ethane diol. And you can see you keep the E so that you don't have two consonants right next to each other, like N and D. Extremely poisonous. This has been, over the last 30 years or so, different places, different times, it has been used in error. You see here it says it has a sweet taste. And people, oh, it tastes sweet. Let's put it in cough syrup. And that's happened. And it's extremely poisonous. It doesn't happen anymore, but it has happened. And there are some times when people have done it, what I say, maliciously or purposely, they have done it. They know they shouldn't put that in the formulation, but the regulations didn't, in one country or another, didn't disallow it, so they used it, and many people got sick, and some died when it's been used inappropriately. So it is. So here's a good one. You spill some antifreeze. Don't let your dog lick it up. Don't let the dog lick it up. This will hurt the animal. Okay? And they might like it. They go, oh, it tastes good. That tastes good. Give me more of that. But it kills the kidneys and the liver. This is really poisonous. So animals will, or children, all right, don't let them play with the antifreeze. This molecule we will learn in chapter 17 when we get to lipids. This is the backbone of triglycerides. You can see glycerol. That's where it gets the name. A glyceride has this as its backbone. If the OHs aren't still there, it's reacted and formed something on there, but these are glycerides. So don't worry about that right now. In chapter 17, I will say you need to memorize the name and structure of that molecule, but you can wait. Okay, classification of alcohols. Primary, secondary, tertiary alcohols. You saw these terms come up in chapter 10, yes? Right? Remember? And I said, you can ignore this for right now. It talked about a primary carbon, a secondary carbon, and a tertiary carbon. And I said, we're going to talk about that with respect to alcohols. Number one, you'll understand it clearer. And number two, it's very significant because these three different classes of alcohols react differently. They undergo different reactions. So if I say, how does this alcohol oxidize? First thing you got to do is figure out what classification alcohol it is. All right? So let's get this down. Here's some examples. First of all, methanol is not going to be classified. It's kind of unique. It has no carbons attached to that carbon. You say, how many carbons are attached to that carbon? None. Zero. So this would be a zero classification of an alcohol, but it just doesn't have a class. Ethanol, what we're doing here, we're going to look at where the OH is, the carbon that bears the OH, and ask the question, how many carbons are attached to it? One.
Which one?
Well, how many carbons are attached to this carbon? One. This is the carbon we're interested in because it has the OH, but then how many carbons are attached to it? One.
Two.
This carbon, here's the OH, here's the carbon attached. One, two carbons, this is a secondary alcohol. Here's the OH, the carbon, 1, 2, 3. A tertiary alcohol, or we use this degree sign. 1 degree, 2 degree, 3 degree.
So depending on how many carbons are connected to the carbon that's connected to the OH tells you the type of category it's in.
Right.
Okay.
And just, this is isopropyl alcohol. This is T-butyl, tertiary butyl alcohol. And you can see it is a tertiary. So this is tertiary. This is secondary. And this is primary. Tertiary butyl alcohol. Okay, classify the alcohols as primary, secondary, tertiary. I'm giving you too much help here, okay? I'm giving you a lot of help. But let's look at A. You look at the OH, the carbon it's attached to, and you can see it has two carbons, one on either side of it. I'm not trying to look for my pointer here. We don't count how long this chain is, just how many carbons are directly attached to that carbon, okay? That's what we're interested in. Doesn't matter how many carbons are over here, just how many are attached. So that has 1, 2, so that is a secondary alcohol. Number B, or letter B, tertiary. A, or C. Now, notice on D, what you got there, you've got a cyclobutane, or cyclobutanol, all right? And as a consequence of it being in a ring, the carbon bearing the OH has a carbon on either side of it. All right, so cyclobutanol is going to be a secondary. Cyclopentanol, cyclohexanol,
They're all secondary.
they're all secondary.
So if it's a,
They're all secondary.
so if it has a cycle, then it's a secondary.
Okay, let me give you a tricky one.
Okay.
There's going to be 2 hydrogens on each one of these. What classification is that? Here's the carbon bearing the OH. There's a carbon. There's a carbon. No, there's only 3. There's only 3. All right? There's only 3. All right? So that is a tertiary. So don't just get these little rules in your head and just mindlessly apply your rule. The rule is this. Here's the rule to go by, is right here. Look at the carbon that bears the OH and figure out how many carbons are attached to it. And if I give you a drawing like that and it gets a little mind-boggling, then draw out the structure. Draw out the structure of it and figure out, okay, how many carbons are attached to that carbon? All right, you don't count this carbon. You just count the carbons that are attached to it. No. I could, but I probably don't have time to. So there, let's see, we got this far. Where are we next? Oh, name those. Name those. Name those, and I'll hand out chapter 12 homework and make a comment on it. And I thought there was something I wanted to show you on Canvas. There was something. Well, let's look at Canvas in a second. There should be, I'll pull this up, and we'll just see, well, if there's something there. Oh yeah, it just occurred to me what I wanted to show. What I wanted to show you here. I will get it. let's, oh, I said I'd hand up. I'll hand this homework in a second. Let's name these. All right, we've heard from 3 or 4 of you. I'd like to hear from 3 or 4 others now, okay? I want the whole class to enter into this. Don't rely on Kevin or Leah or anyone else to answer all these, although Kevin and Leah can answer them. I don't want them going to sleep either, all right? So you can all answer, but let's share it. So someone who wants to take a stab at the top one, top left. Go ahead.
5-methylhexanol.
5-methyl.
No, you don't need the one.
Yeah, you do need the one.
Good job.
Hexanol. 5-methyl-1-hexanol. Okay, we need the one because, I mean, it could have been 5-methyl-3-hexanol. The OH could be on the 3rd carbon. So yes, there's 6 carbons there, and if you're going to call it hexanol, tell me where that OH is. Cyclohexanol doesn't need the one because all the carbons are the same, but not here. They're all different. Okay, who wants to do the next one down? Go ahead.
2-methyl-2-pentol.
2.
Never mind. I went to the other one. The one next to the top.
Oh, you're doing this one up here?
Yeah.
Okay, all right, give it to me.
2-methyl-2-pentanol.
Is that good? Yes. Okay, we got a nod. Good. Okay, who wants to do the next one? Down. Go ahead. Go ahead. Go ahead, Train.
Is 5-methyl-2-heptanol.
5-methyl
2-heptanol.
2-heptanol.
Yes.
1, 2, 3, 4, 5, 6, 7. Heptanol. Okay. And the last one. Go ahead, Leah.
This may be wrong, but 1, 2, 3 tripropyl. Is that right?
No, what we do, we take the tri and we put it before the OL. So it's 1, 2, 3 propane triol.
So you don't drop the E?
No, we don't drop the E because it would end up with an N and a T right next to each other. It's only for pronunciation purposes that we keep the E. Like butadiene, we put in an A just for pronunciation purposes. Okay.
That wasn't too bad.
Hang on. All right, here's Canvas.
Oh, yeah.
Leah said, what do we do about study guides? All right, if you go in here, the homeworks are up there, so chapter 10, 11, and 12 homeworks can be printed out again. If you went to assignments, you should see that chapter 12 homework is due on the 14th, and chapter 1, or exam 1 is due on the 19th. Back to home. I'm going to click on study guides. There's a whole bunch of study guides.
Okay.
All right, so there is some questions. There's the questions and answers. I think the answers are attached to the bottom. So if you don't want to be tempted by the answers, just look at the questions and work it on out, and then you can go find the answers. I want to point this out right here. You all need to get familiar with this before every exam. There's another one down here. There's another one that goes from chapters 10 through 15. It's the same. Chapters 10, 11, and 12 are on that other one too. So I'm going to open it up if I can. All right. Chapters 10, 11, and 12. So if you open up this spreadsheet, you're going to see there's 2 tabs in here. There's 2 spreadsheets in this workbook. This is an important one. So if you ask the question, what do I need 3x5 cards of? This should tell you. All right? So let's see. I'm not at the top of that, am I? Okay. So you can see in chapter 10, you need methane, ethane, propane, butane, 2-methylpropane, and isobutane. You need a card that tells you. Pentane, hexane, cyclo. So go all the way to 10 here. Go all the way up to decane, cyclohexane. Here's the substituents you need to know. So you had one molecule that had a common name. Chapter 11, ethene, ethylene. Ethyne, acetylene. Cis-2-butene, trans-2-butene, benzene, toluene, they have the same name. The phenyl substituent. We didn't talk about this, but the OH group, sometimes we have to treat it like a substituent. We haven't yet, but we would call it a hydroxyl. So there's methanol, methyl alcohol, 2-propanol, isopropyl alcohol, 2-methyl, 2-propanol, 2-butanol. All right? So those are, oh, and the other one here is key terms. No, you need to go, but let me get you your chapter 12. Key terms in each one of those chapters. That may not be a comprehensive list, but if you're asked to name the primary alcohol in this list, then you should know what that means. I'm handing this out front and back. I wouldn't go any further than the front until we get to Monday. Don't worry about the back. The back is the reaction.
I know. I'll see you on Wednesday.
Bye, my loves.
Yes, across campus.
So, I will see you guys later.
All right.
Looks like I got another one. No. You won't have it. Sure. Let's check it. Oh, someone was going to show me. You're going to show me your.
So I'm gonna show you something real quick on mine.
Yeah, I need to